In this lecture, we're going to go over the exercise questions for Chapter 8. Let's get started with question number 1. It says, using the data in Table P18, attempt to relate personal savings to personal income in billions of dollars for the period from 1935 to 1954. Part A says, fit a simple linear regression model to the data using personal income to predict personal savings. And that means personal savings should be the Y variable, and personal income should be the X variable, which is our predictor variable. There are 3 items we want to go through. Number 1, test for the significance of the regression at the 0.05 level. Number 2, find the R-squared and interpret this quantity. Number 3, check for autocorrelation using Durbin-Watson statistic. Should you modify your conclusion in part 1? How can the model be improved? Part B says construct the dummy variable for the World War II years. Let x2, which is the new dummy variable, equal to 0 for the peacetime and equal to 1 for wartime. The war years are from 1941 to 1945. Fit a multiple regression model using personal income and the war years dummy variable as predictor variables for personal savings. Evaluate the results, specifically test to determine whether knowledge of the war years make a significant contribution to the prediction of personal savings beyond that provided by personal income. 2, check for autocorrelation. Is the multiple regression model better than the simple linear regression model of Part A discussed? 3, compare the standard errors of the coefficient for personal income using the original model and the model with the dummy variable. Which estimate is more accurate? Explain. All right, so now let's head over to Minitab and start the analysis. Okay, so you can see here we have the years, personal savings, and personal income. Apparently, personal savings and personal income are time series. So that means we are running a regression using time series data. As we've learned in this chapter, when we run regression using time series data, there might be issues with the autocorrelation in the residues. That's one thing definitely we want to take a look. So first, we want to do a simple linear regression model using income as the X variable and saving as the Y variable. So we're going to go to stat, regression, fit regression model. Now you should be here. So response variable should be savings and continuous predictor will be income. And remember, we want to look at Durbin-Watson statistics since this is time series data. So we want to click on results, make sure Durbin-Watson statistic is selected, then click OK. OK again to get the results. Now, very quickly, although the question didn't ask about it yet, but very quickly, if you look at the p-value for the slope coefficient for personal income, it's 0.054. Technically, if we are looking at a 0.05 significance level, the slope coefficient is not significant. So that means basically our model is not valid. Now, if you look at the R-square, it's really low, 19%. That means the model has a terrible fit to the data. Lastly, for DW statistic, 0.41. The rule of thumb is that when the statistic is close to 2, we say there is not autocorrelation problem for the residues. If the DW statistic is close to 0, or much higher than 2, then we would claim there is potential problem. Now for this case here, 0.04 is quite close to 0 in comparison to 2, and therefore I can pretty much tell that there is a problem with the zero correlation in the residues. Now let's go to the individual questions we want to answer. Number 1, test for the significance of the regression at the 0.05 level. We test for significance of the regression basically means we test on the slope coefficient. We're testing whether the slope coefficient is equal to 0, which is the null hypothesis, versus slope coefficient different from 0, which is the alternative hypothesis, we were looking at this p-value. Since p-value is not less than 0.05, that means we cannot reject the null hypothesis, and therefore we'll claim that it is not significant. Part 2 says find the R-squared and interpret this quantity. So R-squared is 19%. It's awfully low. And this quantity just tells us that about 19% of the variation in personal savings can be explained by personal income. Although, intuitively, if you think about the relationship between personal savings and personal income, in general, they should show a strong positive relationship. That is, the higher the income, the higher the savings tend to be, right? Apparently, our model didn't show that. Most likely it's not because they are not related. Most likely it is because there's zero correlation in the residuals. So let's see. Part 3 says check for autocorrelation using the DW statistic. We just looked at the DW test statistic a while ago and decided that there is autocorrelation. Definitely we need to do something to improve the model. So the question also asks, should you modify your conclusion in part 1? And the answer is yes, because apparently when there's autocorrelation, this model is not reliable. We said based on the DW statistic, the model should be improved. In class, in the lectures, we talk about several ways to improve it, and one of them is to do the difference, right? Now, this question actually suggests another method to deal with the autocorrelation in the residuals, which is to create dummy variables as described in part B. That's what we're going to do to improve it. So let's move to part B. We need to construct a dummy variable. Typically, when we learned dummy variable back in chapter 7, I said for dummy variables, if you have the variable that are in categories, Minitab will create this dummy variable for you automatically, right? Now, in this case here, we don't have the dummy variable in categories. For year, the variable year, we still have numbers.
However, we should not treat them the same way as we see the numbers in personal savings and personal income. We cannot do some of the mathematical calculations with years. For example, we can't do adding. We can't add 1 year with the other. We can't do multiplication or division. For us to include the wartime as the dummy variable, we will need to manually create this dummy variable. So let me name it wartime. Then I'm gonna look for the years corresponding to the wartime, which is from 1941 to 1945. So for 1941 until 1945, I will give 1 to this dummy variable. And for the rest of the years, I will put 0. Okay, so the Minitab is similar to Excel. You can just drag it down like what I did. When you highlight one cell and when you put your cursor around the corner, you have to be a little bit careful. It will turn into a solid plus. Then you drag it down, the same number will be filled in for the rest of the cells. So there we go. That's our dummy variable created for wartime. Now we are ready to run this new regression model using both personal income and wartime as the independent variables. We will go to stat, regression, regression again, and fit regression model. Now personal savings is still the dependent variable. Continuous predictors is still personal income. This time we have a categorical predictors, which is wartime. So click OK. Let's examine the new results. We are given 2 equations, one for the wartime and one for the rest of the time in our data. And you can see that the slope coefficients are the same, but the y-intercept are different. Then moving down to this table of coefficients, we will notice that the p-value for both independent variables is 0, which is a good sign. That means both of the independent variables are significant and they are useful in predicting y. We'll come back to this and answer the question later. In terms of R squared, it is much improved. The new adjusted R squared, since we're looking at multiple linear regression, is 82.73. This is a big improvement from 19% in the previous regression model. F-test, since it's multiple linear regression model, we look at F-test, p-value is 0, so that means the model is valid. And finally, let's look at the W statistics. This is 2.0. It's so close to 2 that we can't say there's any autocorrelation issue anymore. So apparently the second model is much better than the first model. Let's go back to the individual questions and answer every one of them. Number 1 says, test to determine whether knowledge of the war years make a significant contribution to the prediction of personal savings beyond that provided by personal income. Basically, we want to test on the slope coefficient for wartime, which is given in this coefficient table. And we've already looked at the p-value. It is 0, so that means for wartime dummy, the coefficient is significant. Therefore, it contributes to the model significantly. So for number 1, we're going to say for wartime is 0, which means the wartime dummy is significantly related to personal savings. Does the knowledge of wartime contribute to the model significantly? Okay. Number 2 says, check for autocorrelation and ask, is the multiple regression model better than the simple regression model? The answer apparently will be yes. So we'll say the DW test statistic is 2.0, which is shown right here, indicating that there is no autocorrelation in the new model. So the multiple linear regression model with the wartime dummy is much better than the simple linear regression model. Number 3 asks us to compare the standard errors of the two models and determine which estimate is more accurate. Since we know that for the first model there is autocorrelation, we can tell that model is not that accurate. For comparison purpose, let's go to the coefficient table and look at the standard error for personal income. In the multiple regression model, personal income standard error is 0.0128 down there. Now going back to the previous model, the standard error for the coefficient for personal income is 0.028, more than doubled. Right? So this is 0.028 and the other one is 0.012. So in the simple linear regression model, the standard error more than doubled. Apparently, that's not an accurate estimation. So for part 3, we can say the standard error for the slope coefficient in the multiple linear regression model is 0.012, while the standard error in the simple linear regression model is 0.028, which is much higher, since we know that there is autocorrelation in the simple linear regression model. We can tell that the multiple linear regression model is more accurate. In particular, I want to point out that when we add the dummy variable, we can better estimate the personal savings based on the two variables. And that's why we can also get a lower standard error for the personal income. All right, so that's for question number 1. Now let's move to question number 2.
John must be owner of several Mr. Tax rental stores is beginning to forecast his most important business variable, monthly data sales. John must be ran a simple linear regression analysis using time as the predictor variable, which is the x variable, and observed a disappointing 0.563, I believe that's the R squared. Since he knew that his sales data have a strong seasonal component, he decided to fit a seasonal multiple regression model. John created 11 dummy variables for the seasonal effect. Since the Mr. Tax data are monthly, he coded S1 as 1 if the data were from January, 0 otherwise. John did this for each month, ending with S11, which was 1 for November and 0 otherwise. John ran the model using all 12 predictor variables, 1 for time and the other 11 representing the monthly season's effect. The results are shown in Table 17. He's not sure whether he has a good model. The model explains 85.9% of the sales variable variance, which is the adjusted R-squared. Next, John generated the autocorrelations for the residuals of the model, which are shown in Figure 14. The residual autocorrelation has a spike at leg 12, the seasonal lag. 3 questions. Number 1, based on the estimation, is there seasonality in the model? Test at the 5% level. Number 2, are you happy with John's regression model? What changes would you make, if any? Number 3, the data John used are from January 1998 to December 2005, a total of 96 observations. Use John's fitted model to generate forecast for January, February, and March of 2006. And then if you flip to the next page, you will see the Minitab outputs together with autocorrelation for the residuals. So this question is kind of different from the ones we had before in that it provides you the results from Minitab. You don't need to use the data to run the regression. I know you're probably more comfortable with that, and I'm sure at this point you are capable of running the regression models. But you are given the results, and this question asks you to read the results and provide your insights. Okay? So number 1, based on the estimation, is there seasonality in the model? Test at the 5% level. Okay, let's move to the results. When we want to test for the seasonality, basically we're asking whether the seasonal dummies are significant or not. So let me go back to dummies and give you a very brief summary of the dummy variables, right? So dummy variables are used to capture categorical variables. Like month, we have not, right? We have January, February, March, etc. They are categories. We discussed that when we have K categories, we want to create K-1 dummy variables, which is exactly what John did here, right? We have 12 months in the year, so he created 11 dummy variables. The last month, which is December, doesn't have a dummy variable representing it. We call that category the omitted category. And that category is represented when all the seasonal dummies take a value of 0. And that's why we don't need a specific dummy for it. For all the dummy variables right here, the corresponding coefficient basically tells us the difference between that specific month represented by the dummy variable and December. So for example, this negative 48,459 basically tells us that the sales in the first month, January, is lower than December by $48,459. That's the idea. So if we are able to tell that some of the dummy variables are significant, then that tells us the sales in those corresponding months are substantially or significantly different from the sales in December. And that tells us there's seasonality. because seasonality basically just captures the variation in sales across different months, and we expect that pattern to repeat every year. And that's the basic idea, okay? So let's look at the seasonal dummies. And we're going to go directly to the p-values. That's the criteria we're going to use. And we compare the p-value with 0.05. If p-value is less than 0.05, we say that corresponding coefficient is significant or significantly different from 0. And that means that corresponding month sale is different from December sale. Based on that criteria, we can say S1, which corresponds to January, S4, which corresponds to April, S5, May, S6, June, are all significantly different from 0. And that means those month sales are significantly different from the sales in December. And therefore, we can conclude that there is seasonality in the data. Even without looking at the dummy variables, based on the description of the question, John knows that his data has strong seasonality. And that's the reason he added seasonal dummies, right? Question number 2, are you happy with John's regression model? What changes would you make, if any? Well, this question actually asks us to evaluate the model. So we're going to need to look at several things. Whatever we are given here, we look at the coefficients to see if they are significant. We look at adjusted R-squared. And we also look at the F-test. And lastly, since DW statistics is given, we also look at DW. Ideally, we also want to look at the residual plot to make sure the assumptions are satisfied. It's not provided. However, there is autocorrelation for the residue, which strongly indicates that there is some issue with it. And to a certain extent, we don't need to examine the residual plots because we already know there is issue. We do need to improve the model. But let's start from the beginning, right? By looking at the coefficient for time, which is the main X variable other than the seasonal dummies, I can tell that the p-value is less than 5%. So that coefficient is significant, meaning that time matters. As time goes by, sales increase. And we also determined that some of the seasonal dummies are significant, meaning we have seasonality. Adjusted R-square 85.9%, which is good. And looking at the F-test, the p-value is also 0. That meaning tells me the model is valid. Lastly, when I look at DW statistic, it's 1.41. It's relatively close to 2 in comparison to 0. So based on DW statistics itself, I might say there's no autocorrelation in the residuals. However, when we examine the autocorrelation graph for the residuals, we do observe very strong autocorrelation at like 12 and somewhat correlation at like 1. So that tells me that although the DW statistics indicates there's no autocorrelation, this graph tells me autocorrelation still is an issue in the model. And therefore, I would say the model still needs improvement. We will need to do something else to better capture the autocorrelation at like 1 and like 12. Okay. Now, in terms of what can be done to better capture those residuals, that actually leads to some more advanced techniques that's not discussed in the scope of our lecture, but we do recommend that a new model should be estimated that can better capture the autocorrelation in the residuals. Question number 3 asks us to do the forecast. And in the past, forecast means you go to Minitab, you just run the regression model or other models, and then you click predict to do the forecast. This is different. And the purpose of this question in particular to make sure that you understand the fundamental concept of forecast using regression equation. When you click several buttons within Minitab, you got the results. That was quick. But also, it's important for you to understand how those numbers are actually calculated, whether you can do it yourself if you are given the regression lines. So that's the purpose, okay? And to do the forecast, what we need to do is we're going to utilize this equation line. Sales equal to negative 35.23 plus 27.52 multiplied by time, etc. Okay? Basically, what we do is we give values for all the variables, time, S1, S2, S3, okay? Now for time, since there are 96 observations, then we can imagine for when running the regression model, the time variable will take 1, 2, 3, 4, all the way until 96 for the observations that's in order. And therefore, for the next observation, which is January 2006, the value for that variable should be 97. And for February, the value for time should be 98. And for March, the value of time should be 99. Okay? Then we need to determine the value for all the seasonal dummies, which actually is not hard because basically if it's January, we give S1 the value of 1 and value of 0 to all the rest seasonal dummies. If it is February, then we substitute S2 with a value of 1 and use 0 for all the rest seasonal dummies. Similarly, for March, we're going to use 1 for S3 and 0 for all other seasonal dummies. Okay? Then you can either use a calculator or Excel, which is my preference, to carry out the calculation for the forecast. So now I want to move to Excel and show you how I do this. So I've already actually keyed in the numbers. As you can see, I basically copied part of the table in the output, which is the same as the regression equation. So I have y-intercept, which is called constant in the table. I'm going to be consistent. Constant, and the next one is time, S1, S2, S3. And I didn't do S4 until S11. The reason being for January, February, March, the value of S4, S5, all the way to S11 will be 0. So they're all gone, and that's why I didn't put them there. I only need the first 3 seasonal dummy variables, okay? And then these numbers in this column are the corresponding coefficient. Now, what we need to do for the forecast is to use the corresponding coefficient multiplied by the value of the variable. So let's do that for January first. I'm going to use an Excel formula to do that. So this, I first put equal, telling Excel that I'm going to enter a formula. So this is equal to constant itself. So I click on constant, which quote that number in the cell. So I want to do constant plus, if you look at the equation is sales is equal to constant plus coefficient of time, I called it B3, multiplied by the value of time. For January, the value of time is 97, so I type in 97. Plus, next is the first seasonal dummy coefficient multiplied by the value of S1. For January, the value of S1 is 1, so I put 1 there. Now, technically, I need to keep going and say, next is coefficient of S2 multiplied by the value of S2, which is 0. So basically, I don't really need to do this, but I'm going to do it for January. So plus the coefficient of S3 times the value of S3, which is 0, since this observation is for January, and hit enter. That's my forecast. Okay. Similarly for February, I'm going to do equal to constant plus coefficient of time times 98 plus, okay, I'm going to skip S1 because the value of S1 is 0. I will use S2 because it's for February and the value of S2 is equal to 1. And that's it. So hit enter. That's the forecast for February. For March, I'm going to do constant plus coefficient of time multiplied by 99. And then plus, this time I'm going to skip S1 and S2 because both of them take a value of 0. Plus the coefficient of F3 times the value of S3, which is 1. Then hit enter. That's the forecast for March. So that's how we do forecast manually. And I believe that's the end of the exercise as well. So that's it. Email me if you have any questions. Otherwise, I will talk to you next time.